Welcome to Cold Steel, the Canadian Journal of Surgery podcast, with your hosts Amir Farouk and Chad Ball. The goal of the CJS podcast is threefold. The first is to highlight the best research currently being completed by Canadian surgeons. The second is to offer educational topics for both surgeons and trainees alike. And most importantly, the third goal is to inspire discussion, thoughts, creativity, and career development in all Canadian surgeons. We hope you enjoy it.
Dr. Amin Madani is the director of the Surgical AI Research Academy at the University Health Network in Toronto. He is an endocrine and acute care surgeon at UHN and assistant professor of surgery at the University of Toronto. Dr. Madani talked to us and showed us some of the work he is doing on AI in surgery, and in particular on computer vision. He really breaks down for us the terms AI, machine learning, and surgical data science, and highlighted some of the promise and challenges for AI in surgery. Dr. Madani, thank you so much for joining us today on the Cold Steel podcast. It's truly an honor and a pleasure to have you on the show. Could you tell us a little bit about where you grew up and where you did your training?
Thanks for having me. Really exciting. Heard a lot about this podcast. Great to be here. So I kind of went all over the place. So I started in Toronto. That's where I did my undergrad. Then went to Western for med school. Then McGill for residency, that's where I did also my research training and my PhD in surgical education. And then I went to New York for surgical endocrinology fellowship, and then finally back to Toronto. So that's sort of full circle, and started as staff here for the past few years.
That's a pretty awesome voyage. Tell us about your endocrine practice now and what your days and weeks look like and what drew you to that field in particular.
Yeah, sure. So endocrine surgery, I think a lot of people ask me like, which organs do you guys deal with? So thyroid, parathyroid, and adrenals. I don't do too many neuroendocrine or pancreatic endocrine disorders. That's more for the HPB folks. But basically, we deal with everything from the full comprehensive care of endocrine disorder, anything from the benign to the more complex endocrine oncology. My bread and butter is things like thyroid nodules, goiters, thyroid cancer is a big part of my practice, parathyroid disorders, everything from primary to renal hyperpara, including secondary and tertiary. Adrenals, we do quite a bit. We're probably one of the more higher volume centers where we do everything from incidentalomas to hormonally active tumors to the more complex adrenocortical cancers, to the big en bloc resections. We try to do more innovative things like here we do a lot of retroperitoneoscopic adrenals, for instance. We do a lot of minimally focused parathyroidectomies, and also we started radiofrequency ablation of thyroid nodules. So that's kind of like our practice for endocrine surgery. We do a lot of ACS as well. I would say I'm probably like 85% endocrine, 15% ACS. And I would say my practice is more like a 50-50 surgical and surgeon investigator type thing. So probably like 1 or 2 hours a week, 1 or 2 clinics a week, and 2 academic days type of thing. Living the dream.
I'm not very good at math, but somehow that doesn't seem to add up to 5 days a week or 7.
We make it fit. We squeeze that extra day into the week.
Not surprised at all. We've had the pleasure of meeting a number of times over the years for interviews and stuff, but I think I've become really like fascinated by your work over the last couple of SAGES meetings where you've had the opportunity to present some of the amazing work that your group and your lab is really doing. And that sort of focuses around, I think, what some people would call AI in surgery. I think there's some terms that you like maybe better than that. And I think rightly so, because I feel like this term of AI or artificial intelligence surgery gets thrown around so much, and it must be galling. Like when I was in Boston doing my master's, I think there was like two terms that got thrown around all the time, which was blockchain and AI, and it used to drive me insane. So can you talk to us a little bit about like when people say AI, what really are we talking about? And in particular, how is that different than machine learning?
Yeah, that's a great question, and you're so right. There's so much hype around the term, and the number of times I see the word AI thrown around when it's not actually AI, it's quite incredible. I'll just start off actually by saying my background actually is not, I'm not a computer scientist or engineer. I think my background has always been in surgical education, in trying to understand decision making in the OR, where the gaps in performance happen. And so then I kind of met like really smart people who did a lot in computer vision and machine learning, and that's kind of how I got involved with it. But anyways, great field. But AI, just to go back to your question, okay, AI is really it's a big term. It's really the study of computer science that focuses on machines being able to perform human-like functions, or functions that are traditionally done by humans, like perceptual functions or decision-making, cognitive functions, and sometimes even surpassing human abilities like superhuman. That's kind of like the AI, the overall study of all this. Machine learning is a little bit, it's a subset of AI. It's the part about AI that has made it so popular, if you will. If you think about traditional programs, if I want to program something, I'm like, you just write a program, a code, I have to explicitly program it in detail. I have to say, for this situation, this is what's going to happen. For that, this is the situation. And you have to program it for all the different scenarios. Machine learning takes a different approach. It's saying, okay, here's a lot of data. I'm going to find patterns in this data to make sense and to be able to make predictions on new data that I have never seen before. That's the kind of essence of machine learning. So they're very different. Machine learning is a sub-form of AI. It's a form of algorithms that are able to perform AI functions, essentially. I don't know if that made sense.
Yeah, it makes a lot of sense. Take us through then other elements or other terms that someone like me doesn't really understand at all. Things like regression, for example.
Sure. Yeah, that's a common question that we see. So there's difference. So traditional statistics is very different from machine learning. So the first thing is the purpose of machine learning versus regression. Machine learning is mainly designed for pattern recognition, making predictions using very large and complex data sets. Statistical modeling is more focused on the relationship between like dependent and independent variables and things like that. The other thing is the amount of flexibility and complexity of data that you can use. So, for regression, you need to specify the relationship for the regression, like whether it's linear or polynomial or whatnot. Machine learning, these algorithms are way more flexible, and they can handle very complex relationships and patterns of data without relying on strict and explicit programming rules or very specified equations, for instance. They can automatically learn from complex patterns and interactions from the data, and it's often using algorithms with numerous patterns and layers within them. Like that's where deep learning comes in, and deep neural networks. And this flexibility is what allows machine learning to handle very high dimensional data, intricate patterns that are very challenging to represent using traditional regression models, like pixels in a data, taking a big mishmash of data that's unstructured. Like machine learning does very well with that. That's where it really excels. For that same reason, regression works very well, with smaller or medium-sized data sets, because that the relationship between the variables is understood. In machine learning, it can't do that. You really need very large data set to make it work. But on the other hand, machine learning excels very well when you have those complex, unstructured data, and take a big mishmash of like image, text, videos, and try to make predictions out of that. So the focus is on prediction and less on interpreting the relationships between those variables. That's regression and machine learning, how they differ.
I think from reading some of your work, and we'll post links to this. If you're watching this on the YouTube channel, it'll be in the description. If you're listening to this on the podcast audio version, we'll put it in the show notes, some links to your papers. But my sense is that you kind of don't like either of these terms, or you prefer to use the term surgical data science. Tell us why that term is maybe perhaps a bit better, and perhaps also what is meant by the term surgical data science.
Excellent. And that's a great point, because I think, regardless of what you do, regardless of what branch of research, you really have to be specific in the terms that you use. I try to stay away from using AI as much as possible when you write manuscripts or you give a talk, because, it's a very big, sort of overarching term. You need to specify exactly what you mean. Like, for instance, if it's a deep neural network, I'm going to describe it as that, as opposed to saying the AI. I'm going to specify the algorithm, the specific type of algorithm they use for that specific research question, for instance. And I think it's important to do that, especially if we're going to describe our research and it has to be reproducible and so on and so forth. Surgical data science is an important term, and I like that term because that, to me, makes more sense from a surgical standpoint, because it's bigger than AI. It's got the application of why we want to use AI into the term. It's much bigger than just AI. It's the overall field of how we use data to improve what we do in the OR. Basically, surgical data science is basically how we capture this vast amount of data from the OR or around our patients. How do we organize it? How do we curate it? How do we analyze it and create prediction models with it, so that we can help us take care of our surgical patients and ultimately improve everything from quality, safety, stewardship, and so on. When I say data, I mean everything from the vital signs, the blood work, the pixels on the monitor during MIS, or fluoroscopy, all the information the nurses type in the computer, about the ASA score or whatever. This is all data. And when you think about today's practice, we have a wealth of data, on patients, and it's up to us to kind of integrate all this data and to kind of use our gestalt on, and make decisions around the patient. That's how we decide in UR. You know what? Things don't look right. Why don't we divert the patient? I say that because I think you're a colorectal surgeon. So that's kind of how we use data science in our everyday life. But fast forward to the future, we want to be able to tap into those modern computational techniques like AI and be able to integrate these avalanche of data to find patterns that we cannot see as humans and augment our abilities. We're looking at surgical data science. We're looking at the seamless integration of these kinds of support tools in the OR that'll kind of make us sort of superhuman, improve our situational awareness and things of that nature. And it's, this kind of data-driven augmentation is everything, the decision-making support during surgery. It could be how to tailor the care to a specific patient, perioperative decision-making, things like that. And I mean, if you can picture yourself in the future, you can see, like, again, going back to the example of whether to divert or not, you can have an AI algorithm that says, based on the pixels I see, based on the lab work, based on all this data, I can make a prediction with 85% probability there's going to be a leak if you anastomose this, and then, help you with the decision support. So that's how surgical data science, to me, is a little bit different from AI. AI is the actual computational techniques that you use. Surgical data science is a study of using all that for the intended applications.
I'm getting a little bit of PTSD you talking about whether to divert this patient or not, because it feels like 90% of my life is deciding this question. None of my patients.
For me, it's the whether or not the parathyroid's there or the recurrent laryngeal nerve.
What you divert? Anyways, okay.
Yeah.
So it's funny because again, you talk about in this paper that you wrote, like you're among many of these great certain scientists on this paper that I think came out of a workshop, talking about the fact that there actually are not that many success stories when it comes to surgical data science, right? Like, for all the hype, where do we actually see, this type of prediction, risk prediction or, decision support? We don't really see it. Like, it's interesting that you talk about specifically about whether to leak or not. There's been all these papers that have looked at the fact that the decision to divert patients probably is more related to the surgeon's personality type, right? Like, are you a risk averse type surgeon or are you not? And less to do with the patient in front of you in the clinical situation, right? And And like that's just one example. And we don't even use very often very simple, basic decision support type tools. So I guess what I'm asking is, why do you think there haven't been that many success stories in terms of surgical data science? And what do you think it's going to take to actually start to really bring some of this work to fruition?
Thanks for mentioning that, Amir. I mean, that's like one of the things that I spend a lot of my time and energy explaining to people, because you're right, there's so much hype out there, and there are billions of dollars being poured into this industry. The amount of dollars invested by VC companies into like the hype of like AI in surgery and this and that is so profound. It's disproportionate. I think a lot of people recognize how powerful this technology can be, but to this day, I have yet to see. I mean, you tell me, have you ever seen AI in the operating room? Despite all the hype, I mean, it's very hard to see. The only area that I've seen it maybe show a bit of a success is in adenoma detection rates for colonoscopy. And you may be familiar with some of the new platforms that are out there where you have, you do your colonoscopy and then you have a computer vision algorithm that basically detects polyps and kind of highlights it with a square so that you can, to tell you there's a polyp, for instance. And even that, even despite all the studies they've done to that, whether or not it improves patient outcomes is still up in the air. Like it may improve your adenoma detection rate, but perhaps these are, things that would never have led to colon cancer or whatnot. So, the AI, we have yet to show the value proposition. And so that's why we need success stories to actually show that it actually can improve things in the OR. And we're not there yet. The stuff that we've done has been a lot of proof of concepts. Like we know we can use AI to do certain things. Like I know I can develop a computer vision algorithm to tell me whether or not a critical view of safety has been achieved or not. But implementing that into the real world, is it going to improve patient outcomes? I don't know. I'll give you an example. One of the things that we're working on is creating. So all these proof of concepts, they're just a piece of software right now. It's just a software. Taking that into the operating room, it's a big step. Nobody's really done implementation or developed sort of like a seamless tool that people can take in the OR. You can't expect people to buy expensive hardware into every operating room around the world. So one of our work has been in trying to design systems that people can take, like for instance, their phone or their tablet and just put it on the monitor and get like the AI to kind of like give you a an assessment, for instance. Things like that are what's going to help disseminate this kind of technology, making it seamless, making it easy, making it scalable. But even then, we have to be able to show that there is value behind it. And so far, I don't think we've done a good job of that. It's hard to show that an algorithm that tells you where to go or where not to go during lab chole is going to improve bile duct injury rates. Doing a randomized trial on that is quite challenging, as you know.
It's so interesting. I'm glad you took us there. Let's see if we can go a little bit deeper on lap chole in particular, given that it's one of those procedures that's really the glue across general surgery and a lot of our listeners. You guys wrote a recent paper that was super interesting. Can you talk about go, no go, and how, you framed it beautifully, but how that really works in terms of its mechanics and where you see your vision at the end of the day, maybe ending up?
Sure. Yeah, that was so I think just to take a step back, and I think this is where it's really important. I think we can't get, just like any innovation, and I emphasize this to everyone who wants to do this kind of research, don't get sucked into the hype of the technology. First understand what the unmet clinical need is, and then design the solution around that. And that's how we design Go No Go Net. So a lot of my background is understanding how injuries, how decision making and lapses in judgment and things like that. And one of the main cognitive behaviors that we know that lead to bile duct injuries is this lack of awareness, perhaps, or errors in judgment, where you dissect in a in a territory where there's a high risk of bile duct injuries, below sort of this line of safety, Rouvier sulcus and things like that. So we trained an AI algorithm. We wanted to keep it very practical, something very practical that helps you during surgery. So we said, okay, it would be great to have an algorithm that kind of tells you this is the fly zone, this is the no-fly zone. Very simple binary, go, no go. You want to keep your dissection, do whatever you want, but just keep it up there, above this line, imaginary line of safety. That's important because, and that was a big step because for the first time, we're not just developing an algorithm that can tell you, hey, I see a cystic duct. Well, great. How is that helping me in the OR? If I've dissected the cystic duct, I don't really need an AI to tell me that. For the first time, we're training something to do something very clinically relevant. The second thing is that there aren't very clear boundaries around a go and a no-go zone. It's a very conceptual thing that takes a lot of experience, a lot of pattern recognition, gestalt of understanding what a safe zone is. So that was one of the challenges in machine learning that hadn't been done before. So that was kind of like the reason behind it, and I emphasize that because people don't really recognize that addressing an unmet clinical need is a very big part of designing an AI solution. So okay, so we decided to train an algorithm. We said, can it replicate the mind of an expert surgeon to decide where these go and no-go zones are? So the way we did this was we basically we use something called supervised machine learning, which is basically you say, okay, AI, I'm going to teach you how to visualize this part of the anatomy. I'm going to give you hundreds of thousands of different examples. So in this example, this is where the go zone is. This is where the no go zone. In this example, this is where it is, and this is where it is. And you give it so many examples that it can learn from. And eventually, after hundreds of different cases and different scenes from those cases, it's able to figure out that this pattern of pixels, this is where the go zone typically tends to be, and this is where the no-go zone is. And so that's kind of how we trained the AI algorithm. And where we're able to find out is after enough training, it's more or less able to kind of figure out where these go zones and no-go zones. And so it's kind of like your mental model as a surgeon being reflected on the surgical field. So you got this kind of augmented reality thing where it highlights these safe zones and unsafe zones during surgery. That's kind of the idea and the motivation behind that.
So I mean, I don't know if it's okay with you or not, but maybe you could actually share your screen with us, and I'll just enable that for you. But maybe you could actually show us a video, because I think, like I remember at just the recent stage of standing there watching these videos that your students presented, or your lab members presented, and just thinking, wow, this is cool.
Sure. Can you see my screen?
We can.
Okay, so this is an AI algorithm during a lap chole. So this is the idea of go zone, no go zone. So the green is the fly zone, red is the no fly zone. And so for every single frame of this video, the AI algorithm is making a prediction based on this pattern of pixels in the field. This is where I'm predicting as the fly zones and no fly zones. And so you can see kind of it's like this is my reflection of my mental model on the surgical field right now. And so that's the kind of idea behind that. So you can picture this in the operating room if somebody wants decision support, or if you're trying to take a trainee through a case. You can also use this for education purposes, like analyzing your video, your post-operative analysis, things like that. It's kind of like, this is how I describe, where to keep your dissection to trainees. It's like basically reading my mind in a way. I want to show you another video that I think might be of interest. So this is the AI algorithm. So the go zone is highlighted in a heat map up there. And so this is actually a video of a bile duct injury. This is the idea behind this technology, just to give the perspective of how it would look like. So you can see the AI saying, keep your dissection high up on this inferior edge of the gallbladder up there. And you can see that, unfortunately, they're dissecting a little bit too low there. This is the common bile duct. But you can see the AI keeps saying, like, keep your dissection up there. And so, unfortunately, you'll see here, there's clips placed on the common bile duct. A bit of a painful video to watch. And then they end up dividing that. So this is how I see this technology being used. You got an algorithm that tells you, maybe there could be like an alarm system if they see any tool tissue interactions happening outside the suggested region, for instance. So this is what it looks like.
So presumably, I mean, like for this specific video, that was, you didn't tell the algorithm that there was a bile duct injury here. This is, you're showing this new data that's picking this up.
Exactly, like the essence of machine learning. We didn't train it explicitly for that video case. We trained it on all these examples, and now that it's seeing new data that it has never seen before, it's able to make predictions. That's the whole essence of machine learning, and why it's become so powerful of a tool that we can use.
So what did this mechanistically? I mean, obviously, I'm not a computer scientist, so I'm sure even if you tried to explain to me how this was
Neither
developed,
am
I
I.
wouldn't understand. But like mechanistically, what did this look like? So how many videos did you have? Do you have to have someone actually sit there and annotate or tell the like, was it like a per frame? Like you had to tell the, label and annotate it? Like how much work went into being able to develop something like this?
Yeah, it took a lot of annotating. So yeah, so basically what you do is you take these videos and you use there's annotation software that we use where you upload these videos, and it takes very select frames or frames that you tell it in advance. And then you take your stylus on your tablet or your cursor on your mouse, whatever you have, and you highlight the region of interest. And then you do that for all the frames in your data set. And then you say, okay, deep neural network, these are the examples that you're going to use to train yourself. And then you test it and you validate it on a new data set that you've also annotated as well. And it takes a lot of annotating. So as you can imagine, it takes a lot of annotating time to do hundreds of videos. So that's kind of one of the big limitations. You're trying to train an AI to be able to replicate the mind of an expert surgeon. So it means that you got to have expert surgeons doing the annotating, the teaching of the machine learning algorithm, which can be a big limitation. So yeah, so this took us a while to be able to do that. But eventually, we got through. Now, there are new methodologies in machine learning that allow you to, just do a few frames and then have the sort of preliminary algorithm self-annotate on itself. So you do kind of a few, and then it kind of learns like, yeah, I think I figured it out. I think this is where this structure and that structure, and it annotates on itself. And then it has more data set to teach itself as well. So it's kind of like, it is called semi-supervised learning. That's one way we can do that. But you need a very robust methodology, just like any other area of surgical research. You have to have a good methodology, and it has to be nice and robust. And so for this, what we did was we said we created defined start and stop times. So it was from the very beginning of the dissection of the hepatocystic triangle till the moment where clips are placed, in the hepatocystic triangle. So it's really just validated or trained for that portion of time. And we basically took that and divided into 10 random frames, throughout that area of dissection. And so we did 10 frames for video. So we had about 3,000 annotations, and then also go and no-go zones and anatomical marking. So we had about 10,000 annotations to do this.
That's so cool. Not to be negative about it, but where are some of the flaws and some of the places where this approach and this technology falls down, and how do you address that? How do you recognize that, and how do you kind of engineer around that?
No, I did not negative at all. I think you have to be like, you got to be negative and critical about your research. Otherwise, how do we develop good, robust, things from this? There's lots of deficiencies, and we got to be honest, because it's not ready for real time, prime time use yet. So there's a lot of problems we've noticed with the algorithm, that the go no go net algorithm. There's a lot of also problems in general with AI and deep learning. So I'll just start with the algorithm itself. One thing that we noticed, which was really interesting, is as I was analyzing videos, I came across a problem. And this is such a great illustration of one of the deficiencies of deep neural networks. Deep neural networks are designed to basically, like I said, take big, complex data sets and find patterns. and then make predictions. And sometimes it takes the easiest path to find those predictions. So one of the problems we found with this was the AI. We found that every time you had an instrument in the surgical field, it was biasing the results. And so it tended to move the go zone around where those instruments was. So a big question became, wait a second, is it telling you where the go zone is based on the underlying anatomy or based on where the instruments happen to be? It just happens that most lap choles, the instruments happens, the dissection tends to happen in a safe zone, as opposed to an unsafe zone. So is it just learning the wrong thing? And so we had to kind of accommodate, make adjustments to the model based on that. That was one bias we noticed. Another one we noticed, and this is one of the areas where Go-No-Go-Net doesn't fully succeed, is whenever you don't have good exposure of the anatomy, it's not able to tell you properly, like, this is the safe area or this is unsafe area. When the gallbladder hasn't been retracted properly, it doesn't, just like us humans, like I can't properly assess where it's safe, where it's unsafe when I don't have good exposure. And this goes back to training an algorithm for a very specific function. Ultimately, it's not going to be one silver bullet AI algorithm that's going to solve bile duct injuries. It's going to be a library of algorithms that can replicate many cognitive behaviors, like good retraction, safe zone dissection, critical view of safety, like all the different things and nuances that make you a safe surgeon. So that's one of the other deficiencies we noticed. And then the other one was just like, again, like a surgeon, whenever it was so zoomed in that it just sees like fat and fibrous tissue, it had this sort of tunnel vision where it had no idea where it was. And it's like, sure, go there. And it was like, no, not in a safe place. So the algorithm doesn't work well when it's kind of very zoomed in. It has to, see its anatomical, just establish its bearings a little bit. And newer models that we're using are actually integrating memory into it. So it's not looking at individual frames in and of itself. It's looking at, based on frames I've seen previously, okay, this is not actually a go zone, even though I'm zoomed in. So deep learning has a lot of deficiencies, a lot of biases, and you just have to be really, really careful on how you use this technology because it can introduce biases that you never have thought of before. And going to the, AI in general, not just its biases, but there's a lot of problems with it. Like, for instance, how do you people want to know. So if something tells you this is what I recommend, you want to know why. Like, why do you think I shouldn't divert the patient? Well, because of this reason and that reason, to help us and to guide our decisions. This explainability is one of the big lacks in AI. It's kind of like this black box where it's really, really good at making predictions, but it's not really good at telling you how it arrived at those decisions. And so there's an entire field of explainable AI that's trying to target that so that, so if I'm a surgeon and I'm using this kind of algorithm, I can have some explainability around it. And there's going to be more trust, around this kind of technology for people who want to adopt it in their OR. And so that's definitely one of the big problems. Another problem is generalizability. So if just because I train an AI algorithm from data from my institution does not mean it's going to work as well at your institution or even across the street. I'll give an example. Let's say you train an AI algorithm to tell you where to go or where not to go during a, colorectal operation, and you trained it on, you laugh, but that's actually one of our next projects. But anyways, you train it up to do that, and you basically train it only on, University of Calgary data, and you've used only one platform like Storts or Olympus or whatever. The video itself is very different from another platform. So it's guaranteed actually that it's not going to perform as well in someone else using a different platform, for instance, or using a different resolution, different aspect ratio, or somebody likes to have the full view with the black circle around, the circle. Somebody likes it zoomed in so that the full, all these nuances are very important. So you want to train an AI algorithm, it's important to have a very wide breadth of data, real world data that you're going to see. You want data from many institutions, from different healthcare systems, from different platforms, people from different different anatomies, different demographics, people that use different instruments, different techniques, and so on. Because that's that generalizability is a very big key part of it.
I mean, like you mentioned, your background is in surgical education, and I remember you actually came to Calgary promoting the Fuse platform when I was a resident. That's all about surgical energy and stuff. And so, I wonder in your surgical education brain or with that lens on, where do you see this fitting in from an education perspective? Because, in some like the explainability piece, I think is a big in some way, I don't know if you can say it's a problem, but it is a challenge in that, you know, a lot of the things that you're talking about in terms of what the AI has trouble with, like those are also human challenges that we have to learn as trainees. Like I'm reminded of Dr. Ball and I, one of our mentors, Francis Sutherland, he talks about this bile duct illusion, right? And so when you do a lap chole with him, he makes you like have it zoomed out. Like he doesn't allow you to actually move the camera in closer when you're doing a lap chole because of this issue. And so I just wonder, like, do you think, I guess my question is, how do you see this? Where do you see this being implemented in actual surgical practice? Is this something like you switch on at the end of a case to sort of before you put the clips on to give you an additional data point? Is this something you have on all the time? Where does that interact with training? Like where does it behoove us to like actually train ourselves to recognize these problems and these issues? And how does that interact with these types of algorithms and platforms?
That's a great question, Amir. And I don't know if we have all the answers to that. I think we're just kind of seeing this starting to be introduced into the OR, and we've started doing surveys and qualitative studies and needs assessments, surveys, and things like that for end users to kind of figure out how they want this technology integrated. I think that there's kind of two main themes that that you can kind of see this. And when I say AI, I think I just want to emphasize we're talking about a lot of the work that we're doing, computer vision. AI, like you said, can be used so many. You can make prediction models on whatever data sets you want. It can be for perioperative decision, intraoperative navigation, and things like that. Our areas has been really focused about in the operating room, an algorithm that kind of gives you navigation and guidance. So for that specifically, I think that there's sort of two themes that we've noticed. One is intraoperative deployment, and one is postoperative on the videos that have already been recorded. I can see this being used in a number of different ways for educational purposes, for quality improvement, for feedback, for assessment, for coaching, and it ultimately depends on the end users and what their use case is. Like a lot of people are not very keen to use this in the OR, we've noticed, especially since this is a very new technology. There's not a lot of validity evidence behind it and things like that. But they're very happy to take their recorded videos, sitting on their computer and seeing what the AI told them to do, told them they would have suggested, and analyze their performance, and then use that as sort of like an educational experience. Or you can use it for residents as well. Perhaps they can get a safety score of some sort. You can use this for video-based assessment of residents, and we're actually doing a randomized trial right now using this for residents to see whether or not it actually improves their performance. Do they become safer? Does it change their practice and things like that? So I think there's a huge opportunity for post-operative integration. The second piece is intraoperative, and that's been more challenging, obviously, because you have to integrate a technology in the OR. It's got to work with the OR workflow and the equipment and the nurses, and that's a bit more challenging, and we're not there yet. Like the way we've kind of done the initial deployment was we design a pipeline where I can take the laparoscopic tower, plug it into my tablet that I'm talking to you with right now, and basically like have the video feed from the tower on my tablet and get the AI on a monitor. But who's going to have who wants to have another computer in the room, having them guide them? Like that's just not really well integrated into your workflow. So the question begs, so how would you use this in the OR? So I think that if for some people, it may be the situation where they don't want to invest extra hardware to have this integrated into their OR, and they just want a quick like assessment to say, hey, am I on the right path? Yes or no. Okay, I don't need it anymore. Let me continue the surgery. So you can use it that way, like the example that I gave, where you can take your your iPhone or whatever, take the camera on it, put it on the monitor, and then just get the AI to give you an assessment. That's one of the ways we see this technology as being scaled every operating room around the world. Another way is there's going to be a need for some people who, especially when algorithms become a lot more powerful, to have a sort of plug and play solution where you literally plug the AI into the monitor or into your integrated OR, and it gives you on demand high performance AI inference in the OR, and you can turn it on and off whenever you want. Now that begs the question: people who are doing unsafe maneuvers, they're oftentimes unaware that they are doing unsafe maneuvers, and they may not have the awareness to turn on an AI, algorithm to guide them either. So a lot of questions remain. I don't know. I don't think I have all the answers, but I think, in my opinion, we're going to see AI sort of integrated as sort of like a fly on the wall, kind of watching you. If it sees something that you're about to do something, maybe give you like an alarm of like, hey, just maybe rethink what you're doing. Try this instead, or maybe you should bail or change your approach.
Yeah, it's fascinating to think how things might look in the future. I mean, how did you build a team, or because you mentioned, as you mentioned, you're not a computer scientist. So how did you build a team, and talk a little bit about your research group and your lab, and how did that kind of come to fruition, and how did you integrate these different members to come up with such a complex and a high level kind of solution to a very challenging problem?
I think it's yeah. So my background is in surgical. Like, actually, my PhD was in things like qualitative research, exploring people's decision making, understanding what the mental model of an expert elite surgeon. How does their brain work? Let's map it out. How do they think? That was so fascinating to me. And then we did a lot of that, and we're like, okay, great. Now, how do I get people to think like them? How do I get people to adopt a mental model that reflects that expertise? And that's where we started developing educational tools. So initially started off as I developed a software in my PhD where you have a video and it stops, and then the trainee is supposed to say, okay, where do you want to dissect? And they kind of draw. They're like, this is where I want to go, and then it compares it to what experts would have done as well, and they get a score. And I didn't realize this at the time, but I was actually developing an annotation tool for computer vision. And so I showed this to some of my colleagues, and they're like, that is so cool. We should use these annotations to train an AI algorithm to tell you where to dissect. And that's how it kind of all started. So it was a little serendipitous, but I think it's about being very honest about what your skill set is and really sticking to that. So my skill set is in really understanding clinical use cases, the unmet need, designing a methodology that really reflects that problem, and designing a solution around it. And so I never really invested any time in becoming an expert, in programming, coding. I still don't know how to use Python. Like there's no point. Why would I invest all of that energy doing something that it's going to get me only a little bit marginally close to doing what I want in the end? So what I've done is I've invested a lot in creating a network of collaboration. So we collaborate with, at our institution, we have a lot of very smart data scientists, just like they have in a lot of institutions. And I've created these bridges with them where we create these collaborations where I say, okay, we do the surgical part, the clinical part, you guys do the technical part. And, in the end, there's always a paper that comes out of it where you could publish something in a computer science. We publish the clinical piece, and everybody's co-authors, and that kind of collaboration proved to be very powerful and allowed me to kind of outsource that skill set that I didn't have. And that's what it is, right? We're using surgical AI in the operating room. We're cross-pollinating expertise. You can't expect myself, I can't expect myself to become a technical guru, but I know enough about the technology to design an annotation methodology that makes sense and that's going to give me the deliverables that I want. So that's kind of the mentality that I went with. And the way our lab is set up, it's called the Surgical AI Research Academy. Anyways, a little plug for that. But anyways, so our research lab is set up in a way that it's kind of like a enabler. So I work with a lot of different divisions now. We have collaborations in thoracics and neurosurgery and plastic surgery, literally every subspecialty of surgery I work with now. And I don't kind of position myself as the PI anymore. I'm just kind of like the methodological support person for that area. And I sort of provide the necessary infrastructure and support so that I can allow my collaborators who have the content expertise to really guide that for their specific area. And so that's kind of how I position myself. And we got a lot of this is a new area, so there's a lot of like really young investigators that are very motivated. So we have a lot of sister laboratories like all over the world, from Japan to France to San Francisco, Philadelphia, like really all over the globe. And so it's really like a small community.
Yeah, it's so neat, and you just get the sense, like even at Sages, when the surgical data science committee gets together and the group get there, it's just a bunch of very excited and passionate people. So congratulations on all that you've done. Listen, if someone's interested in AI in surgery, what advice do you have for getting involved? What resources are out there? What do you tell, where do other than joining your lab? And again, we will put the links to this in our show notes. What advice do you have for people who are interested in this field of research?
So I think that obviously it depends if they're a trainee or they're an established surgeon in practice. For trainees, I would seek mentors in the field for sure. It's a very diverse area, surgical data science. If you're interested in computer vision, seek people who do that kind of work. Seek mentors that have experience in this area and join their lab or pick up a project, or just sort of join that circle, join the conversation of these different things. It's a very diverse field. So, you can do everything from natural language processing, you can do computer vision, you can do, perioperative risk prediction, whatever your area is. Find somebody who has a little bit of background in that and kind of, help them kind of guide you. And I think the same thing goes if you're a surgeon in practice. I think find collaborators near you that are willing to kind of mentor you, provide you with some guidance. Like, let's say that you're a surgeon in a hospital and you have a big data set and you want to answer a specific question that's important for you. Go to your local person who does that has experience in machine learning and say, hey, I have this data set, like let's work together. I think that's really how things have started for me, and that's how I recommend most people to do that. And honestly, the community in surgical AI is like very keen. It's a very motivated field. So people are always looking for data sets. So there's no shortage of people with the technical expertise to help you do that. And I think the other advice that I would say is focus on what you're good at. Don't try to learn unless you really are motivated, then by all means do it. But learning how to do machine learning from a technical standpoint, personally, is very, it takes a lot of time, and to do it properly is also challenging, and it takes a lot of resources too. You need to have the right computing equipment and things like that. So my advice is try not to kind of go down that rabbit hole too much. It can be a challenge. In terms of how to, what resources, there's so many resources. One of the textbooks, the only textbook in surgical AI that I know of is written by one of my colleagues, Dan Hashimoto, out of UPenn. And so there's a textbook on it. But that was published probably about 2 years ago. Now, the field is changing a lot. Like ChatGPT was not out when that was published, to give you an example, and that has completely been a game changer for so many different things. My advice would also be to pick up some review papers. Review papers are really good. Usually they have more updated data. We actually have everybody who kind of onboards in my lab, they have like a reading list to go through, and I kind of make them go through that before we start diving into projects, because it's important to kind of have some background. The other thing is there's also online courses, but and actually every institution has like jumped on this bandwagon because they've realized it's a good money-making tool. That's actually how I acquainted myself with AI, I'm sad to say. I did it through Oxford University, but there's all these institutions have AI for healthcare tailored courses to kind of, if you don't want to go through a review papers or textbooks, like you have these courses that are available as well. One of the projects that one of my fellows is working on is actually developing a free online curriculum actually for surgical AI. And it's going to be sort of like on a, I guess, probably like a bunch of YouTube videos and lectures on the topics for people, just so that it's freely accessible as well. So there's going to be a lot of like avenues to acquaint yourself with this technology, but collaboration is key in the end, and finding a lab, finding mentors, finding people who've done this before.
So I probably should stop trying to learn Python. Is that what you're saying? Thank God. Thank God.
No. Look, by all means, if I don't want to deter anybody who's really motivated by,
No.
in fact, I love it when people are hungry and they want to learn more, but it's in terms of practicality.
Totally. Okay, we have to, since you mentioned it, what do you think Chat GPT is going to do to surgery? Like, is this
I
just
don't
a
know.
gimmick, or
I
do you
really
or
don't.
no comment?
No, it's look, ChatGPT is a big game changer, but we don't really know where it's so powerful that we don't really know where its applications will lie. But it also has a lot of problems too. Like it's really good at like generating like, like we were joking around with it. I'm like, with ChatGPT, I'm like, write me a song in the style of Taylor Swift about surgical AI, and it like wrote me a song, like, and a really funny song, like it was really good. Like things like that is really good at. It's actually changed a lot of things, like for programming, like one of my the engineers I work with was made a joke. It took him 2 years to train something that one of our proof of concept for 3D modeling and computer vision, and it took him 2 years to write a code for that. When ChatGPT came, it took him literally 10 days to do the same thing. So there's actually a joke amongst computer scientists that the new programming language is English, because you just need to type, this is what I want, and like it'll give you the computer code for it, so you don't have to do it from scratch. You can see ChatGPT used for patient care, like patients have questions about their surgery. They have like a quick thing that they need to answer. Instead of trying to call the hospital to figure out their answers, they got ChatGPT to help them. You can see a lot of potential there. There's a lot of problems too. Like, as you know, ChatGPT will also give you references that it'll make things up that don't exist, which is a big problem. So it's a very powerful thing. I just don't exactly know where it's going to come into play, to be honest, in terms of clinical applications.
It's all very exciting, all kind of nebulous, all kind of interesting. So
The field is
it's
moving
an
so
exciting time
fast.
to be alive.
The
What's that?
field is moving way too fast, faster than we can keep up. Not just in terms of knowing what to do with this, but also how to regulate it as well. So
Yeah, it's a whole discussion for another day about sort of the ethics around this, and what is, how do we roll this out in a way that's safe, and all that kind of stuff. Because I think that is an important consideration, particularly around Chat GPT, but you wonder about the tools that you're developing, how they're going to be implemented. Does that have, what kind of legal, ramifications does it have? Like if your go no go said don't go there, and you went there, like right, like you could see some interesting scenarios coming up down the road, and I don't think we know the answers to any of these things yet.
absolutely, I don't think we have precedent for that. And ultimately, I think it's going to be just like any technology that uses in the OR. Ultimately, you have to use all of that in with a grain of salt and at your own discretion, because ultimately these prediction algorithms have their confidence intervals and things like that, and that's part of what we've integrated into our newer platforms is information about how confident it is about its predictions for you. But anyways, a lot of design considerations that need to go into play.
Dr. Madani, thank you so much again for joining us. It's been an absolute pleasure. One of the questions that we ask our guests at the end of the show is, if you could go back in time and give yourself advice as a chief resident, or perhaps even as an early attending, although you're still probably still a young buck, but if you could go back in time and give yourself advice, maybe as a chief resident, what advice would that be?
Oh, I don't even know. That's a tough question to answer. I think it can be anything, not necessarily related to surgical AI. I think the number one thing I would tell myself is trust your training. I think when you go out into practice, I think there's a lot of unknowns, and you're not sure of yourself. You question yourself, you question your abilities and things like that. I think one of the things I would go back and tell is, it's okay. Like, you got this, you've got the skill set, and you'll be fine. Especially in Canada, we get really good training all around. And the other thing is to not be afraid to ask for second opinions, ask for help. Just, hey, I just want to run this case. This is what I'm doing. I know it's probably right, but just want to run it by someone, and kind of helping that build your confidence so that you can finally fly from the nest, or whatever that analogy is. That would be kind of, I guess, the one advice I would say.
You've been listening to Cold Steel, the official podcast of the Canadian Journal of Surgery. This episode was produced and edited by Kirsten Allen, one of our new team members on the Cold Steel team and a medical student at Queen's University. If you have comments or questions, please email us at podcast.cjs@gmail.com. Thanks for listening.